Use the transfer pipette to fill a cuvette up to the mark, being careful not to overfill. Open the scan program on the computer. Make sure that it is set to scan the appropriate wavelength range for your experiment. To zero the spectrophotometer, prepare a blank cuvette, in this case deionized water. Use a chem wipe to clean the two sides of the cuvette that the beam will pass through once placed in the machine. Close the lid and hit 0. Carefully remove the cuvette and close the lid. Follow the same process for your samples, always remembering to wipe two sides of the cuvette first, but hit start to scan for absorbance. Remember to make sure the spec area is clean before returning to the lab and washing your glassware.
One example of why you need to scan across all wavelengths is to accurately determine the absorption spectrum for your sample, because different substances absorb best at different wavelengths. Another example is so you can determine the identity of an unknown substance. Once you scan across all wavelengths, the computer will generate a graph, and the peak or highest point is the lambda max of your substance. The lambda max is the wavelength at which your substance has a maximum absorption, and it is the wavelength you will use when finding the specific absorbance data for your samples.
The Beer-Lambert law in spectrophotometry states that the absorbance of a sample is directly related to its concentration, so when one is higher, the other is also higher. This is why it is necessary to zero the spec before scanning your sample. Zeroing with a blank containing only what you diluted your sample with, like water, lets the machine know to ignore all the water particles when scanning your sample, so it only measures the absorbance of the actual compound. Forgetting to zero would lead it to measure all the particles, and the absorbance would read much higher than you want. The Beer-Lambert law is represented by the equation. A is absorbance determined by using the spectrophotometer. Epsilon is the molar absorption coefficient, which describes how well each specific compound absorbs the light at a given wavelength. It is determined by dividing the absorbance of a species by the product of its path length and concentration. B represents path length, which is the distance the light travels through the sample and is determined by measuring the distance between the walls of the cuvette. C represents the concentration of the sample and is determined by using the dilution equation. M1 times V1 equals M2 times V2.